Okay, well, I think I'll get started. And first of all, I'm going to just warn everyone that it could be said that I don't know what I'm talking about. And that would be true. But I promised that I'd give this a shot. So here we go. So I'm going to talk today about dark matter and dark energy. But first, let's just remember serious business, which is the fact that we're going to have a full moon in a couple of days. And I don't know if you've noticed the last couple of nights. Of course, today, when I'm talking about it, the weather's terrible. But the last few afternoons, you could really see the moon long before sunset. And the moon is coming up on being full. Tomorrow it will rise at 6:21 p.m. And so in the next few nights, if it's clear, which probably it won't be, look towards the east and watch the moon rise, or see it above the horizon, and then rising about 55 minutes later each night for the next few nights.
Thursday
Um,
looks not too bad, Martha. Yeah,
Yeah,
tomorrow's
maybe. The last couple of nights, it's been really very prominent at 5:30 in the afternoon because the sky's been so clear. And it was high in the sky and approaching being full. So maybe Thursday. I always like watching the full moon, and I'm always disappointed when the weather is bad. That's the way it goes. And this moon is called the flower moon. And we are starting to see flowers even here in Ithaca, New York. Um, this isn't the greatest month of the year to be seeing planets, as it turns out. Venus and Jupiter dominate the evening sky in the west, and Mars, Saturn, and Mercury are visible in the early morning before sunrise, but kind of barely. And there is a meteor shower that peaks on May 5th and 6th. It's not going to be a great meteor shower. And I just point out this website, timeanddate.com. You can put in for any given date, and you can ask it to tell you about Ithaca, New York, and it will tell you what's up in the sky. Okay, those are things that I know something about. So let's go on to the other things. Oh, I forgot this. This was the astronomy picture of the day yesterday. And I just thought I'd show you what satellites Starlink is doing to our view of the night sky. So this is a 10-minute exposure taken with a camera in the from Bavaria in the direction of a comet, which you can see. I hope you can see my cursor there. Shows you the comet. And an amateur astronomer wanted to get a picture of the comet. It's very faint. It's kind of low down on the horizon, right around sunset. And so he exposed for 10 minutes. And what you see here are the trails of Starlink satellites. And this is what is happening to the night sky. And to make it say that astronomers are distressed about this, is to put it mildly. Because okay, you can figure out where the satellite is and you can process it out of your image, but a lot of images have to get thrown away. Um, and it looks like it's only going to get worse. So say goodbye to the night sky, I'm afraid. Okay, so the dark sky isn't dark, but the universe is dark. So I have to define what I mean by the contents of the universe. Well, the contents of the universe is everything that's in the universe. And what do I mean by everything? Well, I mean the universe, as far as we know it, is comprised of matter and energy. And according to Einstein's theory of relativity, those two things are kind of interchangeable. You can think of objects
I'm
as
bringing it.
having energy or having uh, mass. Matter has mass and interacts with other matter via the gravitational force. That's going to be really important to us. Normal matter is the stuff that we're made of. Atoms, electrons, protons, the stuff that we are made of, the stuff that the earth is made of, the stuff that the sun is made of, the stuff that the planets are made of.
Fuck.
That's normal matter. Dark matter we'll define as matter, so it follows the laws of gravity, but it is not visible to our telescopes and, in fact, may not give off any light at all. And by light, I mean radiation, energy related to the electromagnetic force of the universe. Since we can't see it with any kind of telescope, we call it dark. Dark matter contributes about 27% of the universe. Normal matter contributes about 5% of the universe. The total energy in the universe also contains a very minute component due to radiation, light, which has energy. And as I said, radiation, light, energy, and matter are sort of interchangeable when we talk about normal stuff. Then there's this dark energy thing, which turns out to make up 68% of the universe. And that's one of the topics that we'll talk about today. And frankly, we have no idea what dark energy is. I can barely describe it to you, but I'm going to try to describe it to you because I promised David Brown I would. Okay, so let's also go back and talk about the expanding universe and what our picture of the universe is. The current model for the universe starts with an event that took place everywhere in the universe about 13.7, 13.8 billion years ago. At that time, the universe was much, much smaller than it is today, much, much hotter, and much, much denser than it is
What?
today.
I chair.
Can everybody please mute
I'm supposed to
yourselves?
wait.
We're picking up some voice.
Yeah.
Can you everybody mute yourself? Because I can't mute everybody. Okay. There was a tremendous release of energy during that event, which we call the Big Bang. And since then, the universe has been expanding. And what we might think, one analogy for what we mean by the universe is expanding is if we had three galaxies earlier in the history of the universe, those three galaxies today would be further apart one from another. But we could have another three galaxies over in this other corner of the slide, and they would also be moving away, and so they wouldn't be moving away from the same center. Now, what we do know is that the universe is expanding, but we want to also know, what will the universe do in the future? Will it expand forever? Is the expansion speeding up? Will it just sort of expand very slowly, or will it reach some maximum size and then collapse back in on itself? And so that's the fundamental question we want to ask, is what is the history of the universe? What happened in the past? What will happen in the future? And of course, why is that happening? Now, what we also know is that gravity is an attractive force. So anything that is matter that has mass and interacts by the gravitational force is trying to hold itself together. So while the expanding universe is making the galaxies move further apart, at least nearby, gravity is trying to keep them from moving apart, trying to attract them together. And that was the simple picture until the late 1990s. Our idea was that you had an expanding energy due to the Big Bang event, whatever that was, however the event took place, and that gravity was trying to slow down the expansion. But it turns out that's not the whole story, because dark energy exists also. So here's a way of thinking about it. The total amount of stuff in the universe, dark matter, normal matter, dark energy, influences the expansion of the universe. And these snapshots you see on the right-hand side are supposed to show you what happens in a small but large, I mean, small on the scale of the whole universe, but much bigger than the scale of our Milky Way galaxy as the universe expands. But we're only focusing on a small volume, a cube. And a lot of the stuff moves out of the picture as the universe expands. What we know happens is gravity causes local concentrations of matter to collapse. And so as we go from early on, later and later, to the universe today, we see that the universe, parts of the universe have collapsed to form galaxies and superclusters and what we call the cosmic web, because gravity locally causes matter to collapse at the same time that the universe is expanding. So our clues are that earlier on in the universe looked smoother, and this is the universe that we see today. And as we look further and further out, and we look further and further back in time, we see that the universe, if we look back in time, the universe looks fuzzier and then smoother. Now, in these simulations, what you're actually seeing is the dark matter distribution, because as I said before, 27% of the total stuff in the universe is dark matter, only 5% is normal matter. The normal matter behaves the same way that dark matter does because they both have mass and they both have a tendency to to collapse and form denser structures because of gravity. Dark energy doesn't behave that way. So again, what are the possibilities for the fate of the universe? If here we show the separation between galaxies, this tries to show you a universe in 3 dimensions. This is the direction of time. This is the direction of a piece of the universe. The universe could reach some maximum separation. The galaxies reach some maximum separation and then they fall back in on themselves. We'd call that the recollapsing universe. Or we might have a universe that starts out with a big bang and the universe keeps on expanding, but it expands more slowly with time. We call that the critical universe. We could also have something that we call the coasting universe, where the universe will expand forever with little slowdown, or we can have the universe expansion actually expanding faster as time goes on. That's the accelerating universe. The accelerating universe is what we currently believe is the situation our universe is in. And we give it a weird name. We call it lambda cold dark matter. So CDM stands for cold dark matter. And we use this term lambda, the capital Greek letter, as a remnant of something left over from Einstein's role in this story. So when astronomers and even NASA web pages or other web pages that you see draw a little diagram like this that shows you that 68% is dark energy, 4.9% is baryons or normal matter. Baryons are just the word that we use to describe elementary particles that have mass. And dark matter is this. They write it as the density of the real universe relative to the critical universe. Okay, this is I'm messing myself up here. This is the critical universe, the one that just coasts. We don't believe that's the one. We believe that we have the accelerating universe. We like to say that the total amount of density, which we like to write with capital Omega, is the sum of the total amount of stuff contained in matter, a contribution which we call lambda, also known as the dark energy, or the cosmological constant, or sometimes called Einstein's blunder, and then another component due to radiation. The matter, then, which is what gravity contributes, is partly dark matter and partly baryons. But the radiation part is totally negligible. So we forget about that. Our current model contains the contribution of this lambda thing. And so people call it lambda CDM, but what it really means is dark energy plus cold dark matter. And I'm just putting this up here because when you read articles, you go look at articles, people talk about this, and it's completely obscure if someone doesn't say that lambda means dark energy. And actually, some of the clues to dark matter and dark energy are found in elementary particle physics, as we'll talk about. So, another interesting thing I just thought I'd bring up is that in 1920, before we had any idea about the expanding universe, Robert Frost wrote this poem called Fire and Ice about what would happen in the end to the universe. And it turns out he was an amateur astronomer. He was very interested in astronomy. And he had a conversation with a famous astronomer named Harlow Shapley. And they actually talked about what would happen to the universe in the future. And so he wrote this poem. And the idea is that if the universe goes out and reaches some maximum size and then collapses in on itself, you end up with a really hot, dense universe. You end up with fire. If the universe, in our picture, is expanding and expands forever, everything cools down and dies off, and you end up with ice. But he didn't know anything about the expanding universe. And I find it really amazing that he wrote this poem that we now like to show to all our students as showing you the two choices of what might happen to the universe. And it was actually written before we had any idea of this idea of the expanding universe. Isn't that amazing? Anyway, that's just my little humanities lecture on the side. So our idea again is here are pictures size of the universe. Here's the accelerating universe. It's just going to go on and expand forever and ever and ever. So that's where we are. Here's what might happen otherwise. Here's the critical universe. So again, the amount of dark matter governs the growth of these structures in the universe. Here's the universe we think we have. It starts out smooth, and then over billions and billions of years, the structure develops. These other pictures just show what different combinations of the contributions of dark matter, baryons, and dark energy will do to producing structure in the universe. And so if we can observe the structure of the distribution of galaxies or understand where dark matter is in the universe, we should be able to work backwards and figure out how much dark energy there is too. Now, this is a picture of what we call the cosmic microwave background. which is the earliest light we can observe in the universe. The Big Bang occurred about 13.8 billion years ago. About 400,000 years later, the universe had cooled down to about 3,000 degrees. When that happened, hydrogen atoms formed and gave off radiation, and this is what we detect with our telescopes. This is a picture taken by the Planck satellite, and it's an image of the universe at age about 400,000 years after the Big Bang. And what you can see here is, like my pictures that I showed you before, we see that there is some structure. And so understanding this map should tell us something about the structure of the universe 300,000 years after the Big Bang. This is radiation not from stars, not from galaxies, because they hadn't formed yet. It's from hydrogen in the universe. It turns out if we look at the blotches in the cosmic microwave background, they can actually tell us something about the geometry of the universe. Because light rays traveling through space are warped by the presence of matter in the foreground, but also they travel on straight lines in space-time. But space-time is warped by gravity of the mass distribution. And so, in fact, by looking at the characteristic size of the blotches in the cosmic microwave background, we're actually able to figure out that the universe, we call it flat, but what we really mean is that it's critical, including the term of dark energy. And what that means, if we go back to our equation, it means that the total amount of energy sums to the stuff needed to make a critical universe. And it comes about from observing the characteristic size of these blotches. Okay, now what we know is that dark stuff dominates the universe, dark matter and dark energy. As I said, the contribution of radiation is negligible, and so we don't really have to worry about it. It was important very early in the history of the universe, but nowadays it's not important at all. What we're going to talk about a little bit is that we can figure out how much dark matter there has to be in the universe from various ways, only one of which I'm going to talk about. I talked about evidence for dark matter once upon a time. But we can figure out how much dark matter there is because other matter, normal matter, traces the dark matter, and therefore stars in a galaxy or galaxies in a cluster have to know how much dark matter there is in that cluster or there is in that star system. The contribution of dark energy can be inferred from examining the geometry of the universe over cosmic time, how the universe has been expanding. If we can look at those structures and see how they develop, we can figure out how much dark energy is. But let's start with dark matter. So first of all, I don't know what dark matter is, but I can infer that dark matter is there. And my analogy for that is the discovery of the planet Neptune. Neptune, we all know it's a planet. You can't see it with your naked eye, but we could take pictures of it, and we know that it exists. But we didn't always know that it existed. In fact, it was discovered because astronomers were observing the planet Uranus, which is the one just further in from Neptune. And they watched Uranus as it traveled in its orbit around the sun, and they realized that it didn't quite come back to the same place. It seemed to be being pulled on by an object further out. And a couple of astronomers said, okay, we should look in the constellation of Aquarius and we'll find a planet. And lo and behold, they discovered Neptune. So I would claim that Neptune was dark matter until it was discovered, and it was discovered because it exerted a gravitational force on Uranus. So we can figure out that dark matter exists in galaxies because we can watch stars and gas clouds in a spiral galaxy orbit around the center of the galaxy. The same way that the planets orbit around the sun orbits in the Milky Way galaxy. And its orbit is determined by the total amount of matter in the Milky Way galaxy. Not only the starlight we can see, but the dust clouds and the molecular clouds and the hydrogen clouds, all of the normal stuff contributes. But it turns out, in order to keep stars in their orbits around a galaxy, there has to be some matter there that you can't see, i.e., the dark matter. The velocities of the objects around the center, just as in the solar system, the planets move around with very regular orbits, and the speed at which they go around the sun is determined by how far away they are. And if the speed weren't that speed, they would either fly off or fall into the sun. Same thing about a spiral galaxy. The velocities of the stars, as you go from the center of the galaxy further out, have to be set so that the orbits are stable. They keep going around again and again. And that's because the energy made up in the motion of the stars around the center of the galaxy have to balance the gravitational attractive force that's trying to pull in the stars and gas clouds. So we can describe how the velocity changes, this orbital speed changes as you go further and further away from the center of the galaxy. This is what is called a rotation curve. And we have examples of rotation curves. So here we have a little merry-go-round at a playground, a circular disc that you can ride on and get it to go faster. That is what we call solid body rotation. The orbital period is always the same, but the circumference as you go from the center to the outer part grows so that the velocity of that a piece inside the wheel moves in order to go around with the same period has to increase with the distance from the center of the wheel. That's one possibility. Another possibility is what we call Keplerian decline, and this is what happens in the solar system. Remember, 99% of the mass of the solar system is contained in the sun. If we measure the orbital speeds of the different planets around the sun, their orbital velocities decrease as 1 over the square root of the distance from the center to the outer part. So that Jupiter moves more slowly than the Earth, Uranus and Neptune move even more slowly. And so if we look at the rotation curve, we would see Mercury moving the fastest, and then as you go to the outer planets, they move more and more slowly. That occurs because, as far as we're concerned, all of the mass of the solar system is in the sun. However, this is what we observe in other galaxies, and a lot of this work was first done by Vera Rubin, who got her master's degree here at Cornell. And what she and her colleagues found out was that as Whereas in the solar system, the inner planets move faster than the outer planets. In the very center of a galaxy, it kind of looks like a solid body. It's so dense, it moves sort of all together. But when you get a little bit further out, you get a little bit of wiggle here and there, but basically the velocity stays constant. And what that tells us is that the mass is not concentrated in the center. Vera Rubin and Kent Ford measured this for the galaxy and the Andromeda galaxy M31 at about 1970. A few years later, my PhD advisor, Mort Roberts, and his friend Bob Whitehurst measured the rotation curve even further out. And again, this is what's telling us that even as we go further and further away from the center of the galaxy, the velocity is constant. The galaxy, as far as we can see, stops. So we would expect at some point that Keplerian decline to kick in. And in fact, this is what Rubin and Ford suggested, but this is what Roberts and Whitehurst showed with their newer, later observations. So the starlight ends, but there's still matter further out. And then not long after that, a whole bunch of people found out that in all galaxies, this is what happens. So if it exerts gravitational force, so it's keeping these stars moving fast, but you can't see it, it's dark matter. And we now know that 10%, more than 90% of the mass of galaxies like the Milky Way is made up of dark matter. So there is real evidence for dark matter. There's other evidence for dark matter, but I just thought I'd point out we know that dark matter exists, and we know how to measure how much of it there is. So in fact, there's other evidence. If we look at the galaxies and clusters of galaxies, we see the same thing. We can also look at what are called gravitational lenses, where we observe the bending of starlight from galaxies around masses in the foregrounds. They tell us that galaxies have dark halos, which we can't see. We'll also see in a moment, if we look at the structure in the power spectrum of the cosmic microwave background, we need dark matter so that we know that 85% of the stuff we call matter, which is stuff that exerts gravity and has mass, is made up of dark matter. Only 15% of the matter is baryonic normal matter, but in fact, matter doesn't matter. What's important is dark energy. We can throw out the idea. Originally, it was thought, well, there are there are dark matter candidates for baryonic, there are baryonic candidates for dark matter. That would be stuff that we know exists, but you just can't see it with our current telescopes because it's too faint. But we've ruled that out. That's not possible. Instead, we have different weird possibilities for dark matter, all of which are related to elementary particle physics. One is a massive neutrino. A neutrino is a neutral particle which is almost massless, but not quite. And they do exist. We know they exist. We can detect them, but they don't have enough mass to make up the dark matter. There are also things that are predicted by some theories of what happens at very high temperatures and densities called weakly interacting massive particles, but there's little to no evidence of their existence. There are also things called cosmic strings, which have to do with, they call them defects in space-time, some sort of discontinuity in how gravity works. But there's little to no evidence that they exist either. And then there's this idea that maybe we don't understand gravity. Maybe there's something about general relativity and gravity that we don't understand. There's little to no evidence of this, but I'm going to come back to this again. This might be the most promising explanation for dark matter, but mainly only because the other alternatives get thrown out. We'll come back to that in a minute. So the bottom line is dark matter is really important, but it's not enough to explain what we see in the cosmic microwave background size of the blotches. Dark matter makes up 85% of the total matter, but even then, dark matter is not so important. So now we have to go back to a little bit of history. Remember what Einstein wasn't an observer or anything like that. He sat down with his equations. He understood physics. He knew a lot of mathematics. And he essentially said, let me write down the equations that I kind of understand and put in parameters. I know how gravity works. Let me construct a model of the universe that was finite in time. In other words, that had a beginning, um, and contained matter only, because of course he didn't know about dark energy. So he wrote down some equations which explain how the universe, the rate at which the universe expands in terms of the density of the matter with a few other constants thrown in. And then another term that described the curvature of the universe, the geometry of the universe. And so he wrote down this equation and he said, well, this is a nice equation, but gravity causes stuff to collapse. So if I have a universe that can be described by the amount of matter density in it and the curvature, and I just leave it there, it's going to collapse in on itself. And how can that be? We exist. And so he introduced into his equation another term. There's our friend lambda there. He didn't call it dark energy. He just called it the cosmological constant. And he felt about the cosmological constant the way I feel about dark energy. Okay, it's a nice little thing to throw in your equation, but we have no idea what it means. Um, the tuning, the addition of this cosmological constant in the equation was specifically put in there to allow a universe that was not expanding to stay up and not collapse under gravity. Remember, Einstein 1917, that's also before we understood anything about the expanding universe. We didn't learn about the expanding universe until 1929. So the idea of lambda, the history of dark energy, is that it might be some kind of a negative pressure. And in fact, at about 1917, while Einstein was worrying about his equation and how you could describe the universe as being composed of matter that had gravity but also had energy in it, De Sitter also suggested a very different model in which he said normal matter isn't important. I'm just going to have the universe have something that holds it up. I'm not going to worry about it. I'm going to come to the realization that matter isn't the important thing in the universe. So he had the right idea that there was something else there that was more important than matter. Einstein had the idea that matter was a problem for him. Um, it's also important to keep in mind that in 1917, we didn't understand what galaxies were. It was essentially, our universe was essentially the disk of the Milky Way galaxy. The spiral nebulae were noticed as a distinct class of object, but it was not understood how far away they were. In 1931, Hubble was at Mount Wilson with Walter Adams, and Einstein visited them. They took this nice photo op of Einstein looking through the telescope. Astronomers don't look through telescopes, but I guess this was intended as a photo op. And Einstein said, and Hubble told Einstein the revolutionary news that the universe was expanding. It's not clear that Einstein ever called his introduction of the cosmological constant his biggest blunder, even though it's claimed that he did. but he did think it was kind of ugly to have this term in his beautiful mathematical equation that he couldn't really explain. He did tell Linus Pauling that he had made one great mistake, which was signing a letter to President Roosevelt recommending that atomic bombs be made. Okay, so now let's just talk very briefly about evidence for dark energy. There is evidence for dark energy, and the evidence is the way the galaxies are distributed today, that the structure that we see today is best explained if we include in our understanding of the expanding of the universe the fact that the universe expansion is accelerating. And when we go back and look at how the structure has developed, going back from today further to earlier in the universe, that tells us that the universe has been accelerating. We also have the way dark energy, or the concept of dark energy in the 1990s first was brought up again, was that we observe supernovae in distant galaxies, and it turns out that the galaxies appear dimmer and further away than we would expect if the universal expansion was not accelerating. As I said, when we look at the structural details of the cosmic microwave background, that tells us that the total amount of stuff is equal to the amount that gives us a flat universe. And so that tells us that since we can limit the amount of dark matter, there must be another thing, i.e., dark energy, which makes up the rest of the universe. And then the last part is just this cosmological constant that keeps the universe from collapsing under gravity. But all of this evidence, although we can write down and say there's this piece, this piece, this piece, and this piece, it's all circumstantial. Maybe it could be explained by something else, and we don't really, it doesn't tell us what dark energy could be made of. So as I've said, here's our picture of the cosmic microwave background, the earliest light visible in the universe, emitted 400,000 years after the Big Bang. And another way of trying to make a quantitative assessment of the structure at different eras in cosmic time. So here's the universe today. Here's looking back 1 billion years. Here's looking back 5 billion years. Here's looking back 10 billion years. Here's looking back 12 billion years. Is to kind of take a cut through this. The whiter areas are denser. The empty regions or voids are less dense. Let's take a cut through this, and when we do that, we see that we have different scales in the average density. We have a big scale, which we might say is on the supercluster scale. We have a smaller scale, which we might call the group or cluster scale, and the individual wiggles are overdense, underdense regions. Where you have an overdensity, you get a galaxy. And galaxies cluster into groups or clusters or superclusters, kind of like towns, cities, megalopolises, and the entire east coast of the United States. So we can look at these wiggles and understand that over time, they develop more due to gravity causing things to become more dense, but there are other regions that are empty, which we call voids. They are also important because how do the voids form? The voids form when matter otherwise collapses and is pulled away from the void towards the high density regions. But by observing galaxies at different distances from us, at different redshifts, as we say, we observe snapshots at different times. And then we can ask ourselves, what is the amplitude? How much do galaxies cluster relative to the average on the scales of superclusters, hundreds of millions of light years across? And how much is there overdensity when we look at something smaller, maybe 10 million light years across? And that's what we call the power spectrum. And it's a measure of the relative clumpiness of dark matter on large scales versus on small scales. So here's our power spectrum for the cosmic microwave background. We see um, the power spectrum describes how dense structure is on large scales and how it is on intermediate scales and how much it clusters or clumps on small scales. And we get this thing that we call the power spectrum. So this is the large scales, this is the small scales. We're looking at the average amplitude of the fluctuation on these different scales. It's a little confusing, but the bottom line is by looking at how the matter gathers itself together on both large scales and small scales, we get two pieces of important information: that the dark matter makes up 85% of all the matter, and that the universe has a total content equal to 1 in the units that we use of omega. The locations of the peaks in the power spectrum constrain the total amount of matter to be 0.317. The baryons make up 0.049, so 4.9%. 31.7% is the total matter. We know that the dark matter is the total matter minus the baryons, so 0.268. And the total amount of matter is the sum of matter, radiation, and this lambda, dark energy. Radiation is negligible, so we forget that. So this is evidence based on the size of the blotches from the average size overall. This is the evidence based on looking at the details of how the matter structures itself into these superclusters and clusters and galaxies. Different cosmological models adopt different values of omega. For us, omega equals 1. Omega dark is 0.268. Omega dark energy is 0.683. Now, we have to say that we don't understand all of this. And one of the things about this is that this implies that the geometry of the universe is flat. But that doesn't mean that locally this raises a problem for us, because we see that it appears to be accelerating. And we don't understand how the universe can be so perfectly flat. And I just raised the question that this is a real problem for understanding how the universe is expanding. How did the universe get to be flat? Why is it today only accelerating? And so one idea of that is that early on in the expansion of the universe expanded hugely. And while it appears to be flat to us, if we could look at it on a different scale, it would actually turn out to be non-flat. This is something that we call the flatness problem. It's kind of like the Goldilocks problem. Why is everything so perfectly the same? Maybe the universe started out having curvature and ended up being locally flat, so it looks flat to us, but is in fact inflated very early on. Another problem we have is that we can't understand if the whole universe was at the same temperature long ago or today as we observe it. Because while we see blotches in this map, they're actually teeny tiny fluctuations in the temperature, but at the level of 1 part in 100,000. And it means that all of the hydrogen in the universe that formed was at the same temperature. And we don't understand how that could happen. And that also leads us to have problems about understanding this omega equals 1 and everything has to add up. So we have two problems. Besides dark energy, we have to explain why the universe is so close to being at the same temperature and why the universe appears to be flat. That can be explained by a theory that was proposed in the 1980s by Alan Guth and Andre Linde, that at the very, very earliest moments of the universe, so this is 0.4001 second after the Big Bang, the universe expanded by many, many fold. And that's called inflation. And we have not much evidence for inflation, but it's related to our understanding of what happened in those very first moments. So, as I said, there's evidence for dark energy. There's evidence that the universe had some weird expansion history in the very early universe. And what we'd like to be able to do is actually perhaps put the two together. And so I throw out there as an idea, dark energy is supposed to help explain all of the things about the universe that we still don't understand. So what is it? Dark energy is just a made-up phrase that basically tries to explain why the expansion of the universe is accelerating now. It's not even slowing down. We can understand that maybe there was some release of energy 13.8 billion years ago, and that caused the universe to explain. Gravity would slow that expansion down, but that's not what's happening today. It's actually speeding up. We really don't understand what it is. It's really a problem. It really is fundamentally, while we talk about lambda cold dark matter, we really don't understand what's causing it and where we're going. What isn't dark energy? Dark energy is not matter. It does not follow the laws of gravity the way normal and dark matter do, and thus does not have mass, the property that we know and love, that we understand because of theories of gravitation, general relativity. People like to talk about there being four possibilities for dark energy. Vacuum energy, which they also call the cosmological constant, quintessence, defects in space-time, or an unknown aspect of the theory of general relativity that is not understood. And if you go to web pages, if you go to ChatGPT, this is what it will tell you. And that is gobbledygook, as far as I'm concerned, and probably as you are too. So let me try and explain them very briefly in one slide or less. Vacuum energy is a theoretical background energy that fills the entire universe and pushes space outwards. We don't know why, but we think it's related to what's called quantum field theory, which explains some of the weird stuff that goes on in that early fraction of a second after the Big Bang when the universe inflates. It may be that there are virtual particles or pairs of particles that pop in and out of existence. And its interesting property is that it would remain a constant energy over the history of the universe. So that's one kind. I can't explain it better than that. I don't know what it is. But what it's trying to do is explain those very early moments of the universe that we know we don't understand, but where we think some interesting things happen. Quintessence is similar in that it's a strange kind of energy that fills space and behaves in an opposite way to normal matter. So instead of being attracted, it actually pushes things out. But what's also weird about quintessence, which makes it more complicated than vacuum energy and even less understandable, is that it changes, it could change over time and might behave differently over time. So I would say this is the one where you that has everything but the everything in it. It's like mulligatawny soup. You put everything in it that you can find, and you can explain, therefore, everything in the universe. It is dynamic, whereas vacuum energy is constant. We don't understand either one. Another idea is that there's some kind of defect or texture to space-time that we don't understand. We normally think that time is continuous. We normally think that space is continuous, but maybe that's not the case. Again, hypothetical, no evidence for any of these things. And then the last one, which goes back to our understanding about what might dark matter be, is just coming back to the question. General relativity explains how gravity works and how space-time works and how light travels. What if we don't understand gravity? What if there's something about gravity that we haven't figured out? Newton came up with a law of gravity, which then Einstein revised to behave to explain different phenomenon in strong gravitational fields or objects that move at very high speed. Maybe there's something about gravity on very large scales about how it works that we don't understand. So those are my four explanations for what dark energy might be. Um, Again, general relativity predicts the existence of black holes and gravitational waves and other things that we can actually observe, but it doesn't fit into a framework of everything that explains those very first moments of the early universe. So modified gravity is perhaps a lot of people's favorite idea for what dark energy is. And it just says that it means that gravity behaves differently on very, very large scales, on the scale of the whole universe. It's a very interesting idea. There is no evidence that it actually exists. So the bottom line is that I don't know what dark matter and dark energy are, but I am in good company. And so I have a couple of pretty little cartoons here. I particularly like this one, which is they all ask what is dark matter and where is dark matter, but nobody asks how is dark matter. Um, and so I just end there with some cartoons. These are the 21st century cosmological mysteries. And I will only finish by saying that one of the experiments that my young colleagues hope to do with the Fred Young Submillimeter telescope is to test some theories of modified gravity. And so maybe they will actually discover something that will be revolutionary. But let me stop there.